녹화할게요.
Good morning. I am Jeong from Chunam National University. Today's topic is going to be study on electromagnetic wave propagation characteristics in cylindrical Photonic crystal waveguides with high index force.
Okay, let's welcome Jeong 박사님. Okay. Please go ahead.
Content looks like this. First, introduction of photonic crystal structures, and I'm going to explain the proposed cylindrical photonic crystal waveguides. Then, analysis for guiding characteristics of the cylindrical photonic crystal waveguides, and vector wave of FDTD and FDM algorithms. By using those two algorithms, I'm going to give you some results and electromagnetic field solutions, then conclusions and remarks. First, the photonic crystal comes from crystal. Crystal is defined as a periodic arrangement of atoms or molecules. Therefore, the photonic crystal structure, in photonic crystal structure, repeat period is on the order of micrometer. By using this photonic crystal structure concept, we can have a photonic bandgap structure. Photonic bandgap structure is a range of frequencies for which photons are forbidden to travel through photonic crystals in any direction for propagation. This kind of area have triggering very active interdisciplinary researches from around the year 2000. By using this concept, there are so many applications like optical communications, high power operation, such in laser, solar cell sensors, and lots of researches. This figure shows you the proposed cylindrical photonic crystal waveguides. Left one is the proposed cylindrical photonic crystal waveguides reflective index profile. You can see reflective index profile is changing from high reflective index to 1, then it goes up to N1, like this. And the thickness of this R1 to R2 is called as dA. And the thickness of R2 and R2 from R2 to R3 is called as ds, like this. And the right figure shows you some three-dimensional figure for the proposed cylindrical photonic crystal waveguides. The analysis for the guiding characteristics of the proposed CPCW is very difficult because there are so many big changes in reflective index. Therefore, we need to use full vectorial approach instead of a scalar wave approximation to analyze the cylindrical photonic crystal waveguide. I have imposed a perfectly matched layer as a highly effective observing boundary condition at the outer boundaries, like this area. I'm going to impose PML. By using this concept, first I'm going to find the modal propagation constants. Here, the space wave number K0 is 2 pi over lambda. Then we can get normalized propagation constant. This value is also called the effective reflective index. Then we can get electromagnetic field or explosion or effective area. For this research, I'm going to apply 2 methods, like accurate and cross-verified computation analysis of the finite difference time domain and the finite difference method. First, finite difference time domain method, also called the FDTD, comes from Maxwell's method is used for Maxwell's chord equation. Maxwell's chord equation is for source-free and lossless region. For the analysis, I modeled it like this, and this model has electromagnetic components like EX, EY, and EZ, and HX, HY, HZ. So complicated, but we needed to solve this kind of problems and equations. Comes from Maxwell's qualifications, those 2 Maxwell's qualifications. Actually, this algorithm is based on East algorithm, which was researched in 1966. By using this algorithm, we need to apply numerical analysis like FDTD or FDM, like that. For the FDTD, I needed to use central finite difference approximation with accuracy to second order. First, I approximate a grid point in rectangular lattice like IJK stand for I dx j dy k dz. And any function of space and time can be approximated as function over I delta x, j delta y, k delta z, and delta t. Delta x, delta y, delta g are respectively the lattice space increment in the x, y, z coordinate directions, and delta t is the time increment. By using those rotations, we can use those partial derivative into numerical approximation. For the FDM algorithm, also from the coupled Maxwell's chord equations, the following vectorial wave equation can be derived, like curl of curl electric field intensity minus m square k0 square E field equals 0. By using some derivation, we can get Laplacian E vector cross like that, where m is the reflective index distribution, and this m has this kind of variations, reflective variations. Here, I implemented finite difference approximations for spatial derivatives. For more accurate computational analysis, we needed to increase the number of cells, like here. If we increase the number of cells, we can get more accurate result, but there are some limitations because the computer has speed limitation and memory capacity. Based on those concepts, 2 very optimistic cases are considered. for computer analysis parameters. First one is called CPCW1, has R1 equals 0.5 micrometer, R2 equals 0.7 micrometer, dA equals 0.2, like that. And there are total 8 layers. And for CPCW2, R1 equals 1.0 micrometer, R2 equals like that. Only difference is the R1 length. Here, the high reflective index of the core is going to be 1.45 or 1.5 or 1.6. The reason why I am going to use those kind of high reflective index is that high index core can be realized by inserting materials with higher reflective index values than lower pure silica glass. For example, carbon dioxide, liquefied petroleum gas, and nitrogen oxide into the CPCW core. This slide shows you one result for effective reflective index. Those two shows comparison of effective reflective index for the fundamental model. The left one is for R1 equals 0.5, right one is for R1 equals 1.0. As we can see, for the green line, which has the CPCW with NC equal to 1.6 and 8 layers, has more dramatical variation in terms of wavelength. On the other hand, CPCW with R1 equals 1.0 has just almost linearly and inversely proportional to the wavelength. The second result shows you normalized EX field comparison. Left one is for electric field distribution of the fundamental mode at operating wavelength lambda equals 1.3 micrometer for the CPCW1 designed with NC equal N1. N1 has 1.45, and the right one is for CPCW1 with NC equals 1.6. We can see the right one has the energy is more confined at the core because the core has higher reflective index. Also, right one has less discontinuity compared to left one because energy power is traveling at the core. Conclusions. The CPCW with high index cores are first designed and analyzed for accurate full vector electromagnetic investigation. Electromagnetic fields are combined to the core region, and the field decays exponentially in the gradient layers. More significant discontinuities are noticed at the dielectric boundaries for the CPCW with NC equal to N1 compared to CPCW with NC equal to 1.6, which means electromagnetic energy is more tightly confined for the CPCW design with NC equal to 1.6. And effective index result for the CPCW1 with NC equals 1.6 indicate more rapid change compared to the CPCW1 with lower core index like 1.5 or 1.45. Last, the CPCW2 provide almost linearly and inversely proportional results to the wavelength. That's it. Do you have any question?
Okay, thanks for your presentation. Okay.